Now we proceed to study the application of logic to switching circuits. That is, how the logic can help us to represent switching circuits. So here is the simplest switching circuit that we have. It has a battery, a lamp and a switch. So we know that when the switch is closed, the lamp will glow. Okay. So if we represent the state of lamp as L and the state of switch as P, where P corresponds to the statement in mathematical logic, then we can easily see that when the switch is closed, the lamp will glow, and when the switch is open, the lamp will not glow. So closing of the switch is represented by the statement P being true, and opening of the switch means the statement P is false. So clearly when P is true, the lamp will glow, and when P is false, the lamp will not glow. So that means the lamp state will directly be dependent on the state of the switch, that is P. Okay, so this is the simplest representation. Now moving on, we have different terminologies that we use often in different contexts. So we say that it is either on or off, isn't it? That corresponds to the states true or false respectively. Or in terms of binary logic, that means either value 1 or value 0 respectively. Or physically, that means the switch is closed or the switch is open respectively. So that means all the first values are equivalent to each other. On means true, that is same as binary value 1, and that is same as physically the switch is closed. And off means false, that is binary value 0, that means the switch is open. So now let's see the most frequently used possibilities of connection of switches. The first one is series connection. So let's consider that there are two switches S1 and S2. Let us represent them by the statements P and Q, and the lamp is L. Now if you see, the lamp will glow only when both the switches are closed, right? So that corresponds exactly with the truth table of the AND operation. So therefore the lamp state is analogous with the AND operation of P and Q, because in the AND operation we know that when both the values are true, only then the answer is true. So therefore here series connection is equivalent to the AND operation of the two individual switches. Going ahead, we have the parallel connection. So here also let's consider P, Q and L. Now being the parallel connection, we can easily sense that the lamp will glow when at least one of the two switches is closed, right? So this also corresponds to, now we can recollect the truth table of the OR operation. So therefore L is equivalent to P or Q. That is, when at least one of the values of P and Q is true, the answer will be true. So the parallel connection corresponds to the OR operation of the two switches or the two branches involved. Now let's see how does the negation look like in terms of switches. So we use the symbols as shown here. That is, when S1 represents one switch, then S1 dash represents another switch which is in the opposite state of S1. So that means when S1 is closed, there might be some physical arrangement or something by which S1 dash will automatically be in the open state. Okay, so these two are always in the opposite states. When S1 becomes open, then S1 dash will automatically become closed. So if you represent S1 with P, then clearly S1 dash will be nothing but negation of P. So that's the meaning of negation state.